Okay, so welcome back. Um, I'm going to do a couple of examples of SVD stuff. That way we can get on to what we're really focused on with singular value decomposition, which is the applications of it. So, in fact, if you even look at this chapter in the notes, you'll see that it's pretty short and there's almost no exercises because literally the only thing that's covered is how to find the SVD. So once you understand how to find it, then doing it is the important thing about doing it is in the application. So I'll go over that in a second. But first, just to remind you, so SVD. To seek SVD is to take matrix, seek a factorization of that matrix as U times sigma times V transpose. It turns out in the applications that this V and its transpose are going to be most of the time a little less important for us. So what we're really going to be focusing on is U and sigma. But anyway, so singular value decomposition is a factorization of this matrix as the following product, where if you remember, U is an M by M orthogonal matrix. So recall A is M by N. So U is M by M square matrix. It's orthogonal matrix. Sigma is an M by N rectangular diagonal matrix that has particular values called the singular values for the matrix A along its diagonal. And V is an N by N orthogonal matrix. And so I gave a definition of what those things are. But anyway, here was the important bit, which is how to find it. All right, so again, from last time, how do I compute the singular value decomposition? So to find U, the columns are the orthonormal basis consisting of the unit eigenvectors of A transpose. Okay, so I form the matrix product A transpose. I find the eigenvectors and eigenvalues associated to A transpose. The normalized eigenvectors there are, so basically I'm guaranteed that these are going to be orthogonal, so making them orthonormal is just a matter of scaling. So recall, maybe before I list these out, I should remind you of the statements of this theorem, which is that an n by n symmetric matrix has n unit eigenvectors that are all orthogonal to each other, i.e. the matrix containing them is an orthogonal matrix. So I have these facts. So that's true for symmetric matrix, and it turns out that these matrix products are symmetric matrices. They share the same non-zero eigenvalues, and they're all non-negative. Remember that the singular values in questions are formed from exactly those things, so that's why that's important. So anyway, the most important bit for finding U then is this number 2, which is these are symmetric, and so by number 1, I can find n unit eigenvectors that are orthogonal, pairwise orthogonal. So that if I form the matrix whose columns are those eigenvectors, then it's an orthogonal matrix because I can normalize them if necessary, and so those columns form an orthonormal basis. So that's my U, and I call those the left singular vectors. So to find sigma, remember sigma is rectangular diagonal. So everything off that diagonal is 0, and the entries on that diagonal are the square roots of the eigenvalues in A transpose A and A transpose. If what we care about is U and sigma mostly, then I already have A transpose computed from part 1, so this is what I'm looking at. All right, so it's the square roots of the shared eigenvalues between these two things. So the square roots of the eigenvalues, that's my singular values. Finding V is similar to finding U. It's just that instead of looking at A transpose, I'm looking at A transpose A. Okay. All right, so that's how this works. So I didn't do an example last time, so now's the perfect time to start. So example, find the singular value decomposition of the matrix A, which is the 2 by 3 matrix 1, 2, 0, 0, 1, minus 1. Okay. All right. So first step, I want to find U. So to find U, I look at A transpose A. Or sorry, A transpose to find U. So what does A transpose look like? Well, I'll write it out. I won't write it out again. So A transpose, so first row becomes first column. Second row becomes second column. What is this if you multiply it out? So this is a 2 by 3, this is a 3 by 2, so the resulting matrix is a 2 by 2, and it should be symmetric according to that theorem. So this is 5, 2, 2, 2. So indeed it is a symmetric matrix. There it is. Okay. Now, in order to find U, I need to find the eigenpairs for these associated eigenvalues. So what are its eigenvalues? It turns out the eigenvalues for this one are 6 and 1. And here's the associated eigenvectors. So the eigenpairs are as follows. So it's 6 minus 0.89 minus 0.45, and the second eigenpair is 1, 0.45 minus 0.89. Now, here in this example, the way this is written in the notes is that you're already given this thing, both of these vectors have already been normalized, so these are already unit vectors. If they weren't, you would have to make them unit vectors. So these are already unit vectors. Okay, but that won't always be the case, right? So when you are finding eigenvalues, eigenvectors, you're definitely not guaranteed that your eigenvectors are always going to be unit, but you can make them unit, because if you have an eigenvector for some associated eigenvalue, it's still an eigenvector for the same eigenvalue if you scale it by some scalar. So do the typical thing, right? Scale it by its length, and you're good to go. So you are fine here with these two. Okay, so those are the eigenpairs, which means that I can write out U immediately. Maybe before I write out U, I'm going to compute the other things, because I said something last time. I noticed now that I didn't actually write it out when I gave you the description of how to find U, sigma, and V. But I said something aloud, which is, once you've found the eigenvalues here, you can arrange them in any order you like, typically. And so long as you compensate by arranging the corresponding column vectors in U and V to match up, it doesn't actually matter. But by convention, typically this is done in non-increasing order. Okay, so that's the convention. It will become more important when we talk about applications later. So I'll write it out and underline it that's what we're assuming, because otherwise what we're saying doesn't really make any sense. But you'll see that in a bit. But before I write this out, so here's my unit vector. Well, okay, let's go ahead and do this. If I'm going to have these going in non-increasing order, then I want my largest one in the upper left, and that's going to be the square root of this thing is going to be bigger than the square root of 1. And so this one is going to be to the further left. So in order for that to match up in U, my first column of U, so my first column of U is going to be this one. Okay, so maybe I should write that out here. So U is minus 0.89 minus 0.45, 0.45 minus 0.89. Okay, if you're confused about why its columns are ordered this way, when I write this out at the end, I'll explain why this is. So here, saying that U is this at this step required me to think forward a little bit. Okay, so you'll see what I mean here in a second. Okay. All right, so that's U. Okay. So then second part, so same example. I want to find sigma. Okay. So how do I find sigma? Well, apparently this is I can find this by setting it up so that the diagonal entries are the singular values, which are these square roots. Now, I have been told that these are shared. I have shared non-zero eigenvalues between A transpose and A transpose A. So to find sigma, I look at, so A transpose has eigenvalues 6 and 1. Okay, I should write lambda equals 6 and 1. Okay, so the singular values in question are S sub 1, which is square root of 6, and S sub 2, which is square root of 1 or 1. Okay. Square root of 6 we'll say is like 2.45 approximately. Okay. Okay. So then what is sigma? So sigma is 2.45, 0, 0, 1, 0, 0. Okay. All right. Again, if you're confused as to why 2.45 goes in this slot versus this slot, I'll talk about that in a second. Okay. The order is arbitrary, and we are allowed to swap these, but then I would have to swap U as well, the U that I've chosen. So, as I said, I'll explain this when I have it all down on a single sheet of paper. Okay. So that's sigma. 3 is to find V, or find V transpose. Okay, so how do I find V? Well, instead of looking at A transpose, I look at A transpose A, and it turns out that A transpose A is 3 by 3 matrix, reading row wise. This is 1, 2, 0, 2, 5, minus 1, and 0, minus 1, 1. Okay. All right. This has the following eigenpairs. So the eigenpairs are 6 and unit eigenvector minus 0.37 minus 0.91, 0.18, 1 minus 0.45, 0 minus 0.89, and one more eigenpair. That's the eigenvalue is 0. The associated eigenvector is minus 0.82, 0.41, 0.41. Okay. Now, here's something. Notice that A transpose A has 3 eigenvalues, and so there's 3 eigenpairs here, right? But we were told in that earlier theorem that they should be shared, right? But A transpose A actually has 3 eigenvalues instead of the 2 that AA transpose had. So what is the problem here? Well, there's no problem, because in this theorem, we were just told that these things share the same non-zero eigenvalues. So A transpose A or AA transpose may have additional 0 eigenvalues tagged on here, as this one does, but they share the same non-zero eigenvalues. Okay, and that is what is key, because imagine we did this first, right? If we did this first, how would we compute sigma from this info? Well, you look at these eigenpairs and you choose only the non-zero ones, and that's how you determine the singular values. So the non-zero ones are the same as the eigenvalues for AA transpose. So you end up with the exact same computation here. Okay, that's why that's important. Okay, so what's the last step here? Well, first of all, I'm not going to waste the time to write it here. I'm going to write it here in a second. So I'm not going to, I'm not going to write out V transpose here, but how would you build it? V transpose, so V is going to be the correct order of ordering these 3 eigenvectors, and then it's going to be the transpose of that. So so then how does this, oh, actually, is that true, or do I read it off here? Is the transpose already done here? I believe the transpose is actually already done, so that I can actually just write this down as it appears. So this is actually V transpose. Is this V transpose? Actually, yeah, I believe that if I just write these out in the correct order, that I'm good to go. So I'll do that here in a second. Okay, so anyway, how does this work? Then, thus, A is equal to U sigma V transpose, i.e., our A, which was the matrix 1, 2, 0, 0, 1, minus 1. That is equal to U, which is minus 0.89. I'm going to read column-wise. Minus 0.45, minus 0.45, 0.89, times sigma, which is 2.45, 0, 0, 1, 0, 0, times a 3 by 3, which is V transpose, which is minus 0.37, minus 0.91, 0.18, minus 0.45, 0, minus 0.89, minus 0.82, 0.41, 0.41. Okay. So this is U. This is sigma, and this is V transpose. And if you actually were to multiply this out, if you stick this in MATLAB and multiply it out, you'll see that this triple matrix product is equal to this 2x3 matrix we started with. Okay. Now, finally, let me see if I have any questions yet. Nope. And so finally, to explain what it is that's going on here when I kept saying that there was an issue. So quickly, what it is that is going on here is the following. I am actually allowed to arrange these entries in sigma however I want to. So remember, these are square roots of the non-zero eigenvalues showing up as in AA transpose or A transpose A. So I can arrange those along this diagonal in sigma however I want to. But however I do that, I have to accommodate by swapping the orders of the columns of U and V transpose. So for instance, how would this work? If I had written this matrix as 1 0 0 0 2.450 instead, what I would have to do to accommodate, for instance, in U is I would swap the order of these two columns. Okay, and so if this column is, and you can just go back and see, this column arises as the column associated to the eigenvalue 6. 2.45 is the square root of 6. So this entry is associated to that eigenvalue 6. And that eigenvalue is associated to this eigenvector, which is this column. So if I move this eigenvalue to this entry instead, I would have to move this column over here to be the second column. I would just swap the place of these two columns, right? Since I've swapped these orders. Now, the reason why you shouldn't worry about that too much is for our application purposes, it is beneficial to have these go from largest to smallest. Okay, so you want the largest one showing up in the upper left corner, and then going down from there. Okay, that's how you want to do this, and you'll see why when we talk about the applications of this stuff. But this is how you want this to go. Okay. So V transpose, computing this is not that big of a deal typically. In fact, in most of the examples when I talk about the applications, I'm not even going to write out what V transpose is typically, because to understand what it is we want to understand about the data that is contained in the matrix, typically all we need is U and sigma. Okay, so that's how that goes. All right, now continuing on, maybe I'll do another quick example. So one more example of how this goes. So I want to find the singular value decomposition of matrix A, which is 1 2 0 3 1 4 1 1 minus 1 0 1 2. Okay. So first, I look at AA transpose. So look at AA transpose. If I actually write this out, so AA transpose is a 4x4 matrix. So this is 5 5 3 2 5 26 0 9 3 0 3 minus 1 and 2 9 minus 1 5. Now you might say, well, I can shortcut this since I know that this is going to be a symmetric matrix. The second that I have computed the diagonal and this the upper triangular entries, then I know what these have to be because it has to be symmetric. That's true. If you were doing it entry-wise like that, then that's how you do it. But there's typically not too much of a problem multiplying these two things. Okay, so then I can use my favorite program to compute the eigenpairs for this. So don't have enough room to put all the eigenpairs here. So eigenpairs of AA transpose are, I get 30.4702 and some vector that I will call U1, because I'm going to list these in decreasing order, so I'm going to call this vector U1. The next is 6.5221 U2. Next I get 2.0078 and U3. And lastly, 0 and U4. Okay. All right, so there's my eigenpairs. Okay, I didn't list these out. If you want to see these, you can, if you're following along in the Chapter 9 notes. This is on page 7 in Chapter 9. Okay. All right. So next, A transpose A is the 3x3 matrix, 11, 6, 11, 6, 7, 5, 11, 5, 21. Okay. Which has eigenpairs. These are more writable. So the eigenpairs are 30.4702, and the associated eigenvector is minus 0.5380, minus 0.3049, and minus 0.7859. Okay. The next eigenpair is 6.5221. Associated eigenvector is 0.4090, 0.7208, and minus 0.5596. And last eigenpair is 0.0078. The vector is 0.7371, minus 0.6225, and minus 0.2631. Okay, you will note that these three eigenvalues are the same as the non-zero eigenvalues in AA transpose. Okay. All right. So now I need to compute my singular values. So singular values are S sub 1, which is the square root of the largest eigenvalue, so that's square root of 30.4702, which is like 5.52. S sub 2, which is square root of 6.5221, which is approximately 2.554. And S sub 3, which is square root of 2.0078, which is approximately 1.417. Okay. So one, 2, 0, 3, 1, 4, 1, 1, minus 1, and 0, 1, 2 is equal to U sigma V transpose, where I can write the following. So U is equal to those vectors that we listed out before, as I already listed them, U1, U2, U3. So 2, U3, and U4. Well, I shouldn't have commas here. What am I doing? This is the matrix that has those as its columns. So it's the matrix with those 4 columns. Sigma is the rectangular diagonal matrix having my singular values on its diagonal and zeros everywhere else. So this is 5.5200, 0, 2.554, 0, 1.417, and the last row is all zeros. Now, before I move on really quickly, if you're confused about the dimensions here, to keep track of them, we began with a 4 by 3 matrix. Okay, so this is 4 by 3. So the way that this should work is that U is 4 by 4, sigma is 4 by 3, and V is going to be 3 by 3, right? So sometimes it's good to keep track of these things. V is going to be exactly as I've written, minus, maybe I should go back here and say I'll call this one V1 prime, V2 prime, and V3 prime. So writing them in this way, I can read off V as V1 prime, V2 prime, V3 prime. So this is a 3 by 3. Okay, whoop, I'm off camera. There we go. Okay. So, a couple of notes. All right. So, and this is brought up in the notes as well. But this is something that you might notice, is that the eigenvalue 0, right, that can show up either as an eigenvalue in A transpose, or A transpose A. As far as the singular values go, since by definition the singular values are the square roots of the non-zero eigenvalues, we're essentially ignoring the 0 eigenvalue and its associated eigenvector, right? And so what I could do here is, if I just ignored the 4th column of U, so the 4th column of U, remember, was the eigenvector that was associated to the 0 eigenvalue. If I ignored this column, okay, if I just threw out that column, and I also threw out this all 0 extra row of sigma, then what I get is that actually we would still get that A is U sigma V transpose. We would still get this, okay, even tossing that out and tossing this out. And so in a lot of places, when you see singular value decomposition being talked about, what will happen is exactly that. They will do exactly that. They will ignore the eigenvector that comes along with the zero eigenvalue and the extra row of zeros that accompanies it. So so that you still get this decomposition working in the same way. So it's still a factorization in the exact same way, and the like extraneous info is tossed out, right? Because that's not contributing to the singular values at all, since those come from the non-zero eigenvalues. We're not going to do that. I'll always write out this extra stuff, because if you're actually using MATLAB to compute these things, then MATLAB is not going to toss them out. It's going to have them included. So even though it's a little bit inefficient, that's how we're going to do it. Okay, now if you're interested in the actual formal justification for this stuff, you can read the notes. So read chapter 9, pages 8 plus, if you want to see the proof of this justification, or of this breakdown. So if you want to see exactly why this works the way that it does, or at least for a simple case, for the square case, then you should read that. I'm not going to go over that because our entire use of this is going to be purely in its application. So that's the only thing. So out of chapter 9, the only thing I care about is that you understand how to write down the SVD of any given matrix. Okay. All right. So we have a little bit of time to talk about applications then. Okay. So again, this is key. What we're actually interested in are applications of the SVD to figuring out some sort of data that I'm interested in. Okay. This is the contents of chapter 10. Let me quickly check. Yep, hardcore Mountain Dew fans only. That's true. Okay, so this is applications of the SVD to data approximation. Okay. All right. So then what is the idea? Think of a matrix. Let's say an m by n matrix. So let's say we have an m by n matrix as really just containing some data. So think of it as containing n column vectors that we think of as points as Rm, right? So containing n points of Rm. Okay, so these are data points, if you like. Okay, so I have some points describing some data. This matrix contains them. So then what is the idea? Or after this idea, what's the next idea? We wish to use the SVD of A to infer properties of these data points, or of this set of data. Okay. Okay. So the goal, one, to understand the geometric properties of U, i.e. the left singular vectors. And 2, to understand the algebraic properties of the singular values and what it means for our data. Okay. Oop. Okay. And then 3, combine these. To form an overall picture. Okay. That sounds pretty vague right now. But you'll soon see explicitly how this stuff relates to quantities that you've seen in other contexts. Okay. So, a couple of definitions before I go any further. So, first, the variance of a set of vectors is the sum of the squares of the norms of the vectors. Okay, and one more definition. The norm of a matrix which we denote as you would the norm of a vector, but now I have a matrix there instead, is the square root of the sum of the squares of the entries i.e. it is the square root of the variance of the columns of the matrix. Okay. All right. So defined in this way, we can say that two matrices are close to one another if the norm of their difference is very small. Hey, just like we had the notion of two vectors being close to one another if the norm of their distance or of their difference was small. Okay. So, first of all, before I proceed, note V transpose is not going to be important for us for these applications. So typically I won't even write it out. I'll just write it as V transpose when I'm writing out the SVD. Okay. All right, so let's do an example. Okay. So say that A is the following 2x4 matrix. So reading column wise, this is 4, 1, 1, 1, minus 2, 0, and minus 3, minus 2. Okay. Now, what we want to do, following that goal that we set out first, we want to come up with a geometric interpretation for what U is. Okay, and so for this purpose, since I'm thinking geometrically, I'm going to pretend that my matrix A contains these 4 data points, so 4, 1, 1, 1, minus 2, 0, minus 3, minus 2, where I'm thinking of these as being literal points in the plane, right? Order pairs in the plane. Okay, so before I proceed, I'm just going to go ahead and write out the SVD. So the SVD of A is the following. So A is U sigma V transpose, where U is minus 0.9320, minus 0.3625, minus 0.3625, 0.9320. So this is U. So I'll go ahead and call this U. This column is U1. This column is U2. Times my sigma, which is 5.8550. That's an 8. 0, 1.312, 0, 0, 0, 0 times V transpose. So this is sigma. Okay, and with the normal notation that we're using, S sub 1 is 5.855, and S sub 2 is 1.312. Okay. All right. So what do I want to do? I want to draw a nice picture. Okay, so I'm going to draw a picture now. So here's my picture. If I actually plot these points, let me make some hash marks here. Maybe I'm really bad at making equidistant hash marks. Okay, so how does this go? I'm going to plot these 4 points. So let's see, 4, 1, there's one of them. Okay, so there's 4, 1, 1, 1 is there. And minus 2, 0 is here. And minus 3, minus 2 is over here. Okay. All right, so there's my 4 points. Okay, now, what am I going to do to come up with some geometric interpretation of this? So the idea is to, and you might have seen something similar to this when you did eigen analysis in differential equations. You saw something done like this, or just generally when you've dealt with eigenvalues, eigenvectors. So I'm going to write out the eigenspaces associated with these eigenvectors, right? And since here I have single eigenvector, these eigenspaces I'm talking about are just lines determined by those eigenvectors. So I want to look at the line determined by U1 and U2. Okay, and so if I plot those out, what does my line determined like U1 look like? Or determined by U1, what does that look like? This is my U1 subspace. The U2 subspace, what does it look like? It looks something like that. I mean, it doesn't look something like this. It is perpendicular to U sub 1, so determined in the same way, but you know it's perpendicular since U is guaranteed to be an orthogonal matrix. So here's the line determined by u sub 2. Okay, so there's my eigenaxes, if you like, right? Okay, so looking at this picture, so I have these two lines determined by u sub 1 and u sub 2. Here's my data points from A. Okay, what does it look like the geometric significance of u sub 1 and u sub 2 are? Well, what it looks like is that while my points are spread out a lot in the u sub 1 direction, they're not spread out very much at all in the u sub 2 direction. Okay, so what does that mean? What's a nice way of making that more precise? If I were to take these points and I were to squash them down to u1, well, what does that mean in big boy language, right? It means that I'm going to orthogonally project, right? So if I project these points onto u sub 1, then what I get is a bunch of points that are spread out like a good bit, right? So if I look at those points, they're spread out a good bit. They're peppered all over this line. Okay, but if I took these same points and instead of orthogonally projecting them onto u sub 1, I projected them onto u sub 2 instead, what would happen here? So that one goes here, this one goes here, this one goes here, this one goes here. They're all bunched up, right? Certainly they're a lot closer than they would be on the u sub 1 line. Okay, so that's the idea, right? So note the points are spread out more in the u sub 1 direction and spread out less in the u sub 2 direction. Now, in this particular case, it happened that in the u sub 2 direction, they're actually not spread out very much at all. They're pretty close. That's not what happens typically. So typically, all that I get out of this analysis is that they're spread out the most in the u sub 1 direction, and they're spread out, maybe they're spread out a bunch in the u sub 2 direction. They're just not spread out as much as they are in the u sub 1 direction. So that's the main point. Okay. So what does this mean for us? So the idea, right, intuitively, the idea is that I should say something before I write this. Let's go all the way back. I am assuming that I'm setting up this SVD in a way, as I mentioned before when we were doing these examples, where I want the largest singular value showing up here, right, in this first entry. And then I want the singular values to go down from there. Okay, so when they're arranged in that way, what I'm going to say makes sense. If they're not arranged in that way, then none of this is going to make sense because the most spread out direction is going to be some other u sub I, right? So the reason that u sub 1 is the direction they're the most spread out in is because u sub 1 is the eigenvector associated to the largest singular value, right? So that's how this works. Okay, so intuitively the idea is that the points that is the columns of A are most spread out in the direction of u sub 1 and less spread out in the direction of u sub 2 less still in the direction of u sub 3, and so on. Okay, so our example was there was only u sub 1 and u sub 2, but in general, for a different matrix A, the idea here is that if you've ordered those singular values correctly, so that u sub 1, u sub 2, u sub 3 are associated to singular values where you have the largest, then the next largest, then the next largest, in that order, then this all makes sense. Okay. So note that each of these are perpendicular to one another. So this is, in a way, it's saying that how the columns of A are most spread out in perpendicular directions of decreasing importance. Okay. So that, in a way, this is telling you that u sub 1 is the most important, u sub 2 is less important than u sub 1, but more important than u sub 3, and so on like that. Okay. Now, ultimately, I'm going to stop here for today. It's a good stopping point. I'll finish this analysis up next time. Ultimately, what this is going to tell us is we are going to be able to analyze data sets where we are going to be able to say something about the variance of the columns coming directly from the SVD. In fact, you might have already seen how it pops out from the SVD immediately. So anyway, I will stop the lecture here. I'm going to, so for next lecture, you don't have to wait on my link. I'm going to make the links to the lecture public so that you can just immediately, or you can just wait and go to the YouTube channel and I'll start at the normal time, so you don't have to wait for my link. It'll just be public and it'll just start automatically. I'll clean up the YouTube channel so that it's all organized and so that it's not mixed with all of my classes, so that that'll be nicer to navigate. But anyway, that's the immediate plans. Still haven't posted any more homework since since the break. I also haven't updated your grade book, so I'll do all of that soon. When I post the homework, it won't be due. All of the homework I post for the remaining of the semester will be due at the end of the semester. Obviously, it would be better for you in studying and in just keeping up with the content if you did it as we went along, but so that there's no issue with due dates and stacking due dates depending on how your other classes were implemented online. I just thought I would have everything due at the end. That way you can do it whenever you want to. Okay, so anyway, that's the plan. So I will see you all on Thursday at the same time. More or less spread out again. So basically, if you look at this picture, notice that along this axis, these points are spread out a lot, right? What I mean by that is, and okay, maybe I shouldn't say a lot, but they're spread out, okay? So what I mean by that is if we ignored the other component, so if we just projected all these points onto u sub 1, then what we'd have is just a bunch of points distributed. So it would be a point here, 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 and here, right? Would be the points that we would get. So here I can even, so if I project these down and project this one down and this one. So you wouldn't call these points close together in any way. You'd say they're spread pretty far out, right? But if I projected them in the other direction, right? So I took this point and now I project it orthogonally onto u sub 2. So there it is. Same thing here. Same thing here. And same thing with this one. Right? Well, you'll notice that these are bunched together a lot more closely, obviously, than these are. So that's all that I mean. And again, it doesn't have to work out so that these are so close, because it works out so that these are actually like really, really close, relatively. So it doesn't have to work out like that, but it will always work out so that they are closer along U2 than they are along U1. So that's what I meant. Okay, so as I said, I will tidy up the YouTube page, and I'll still, like I said, I'll finalize the syllabus page so that everything is up there. So by the end of this week, absolutely everything will be set. Like I said, you'll have some periodic homework that I'll assign. It won't be due till the end of the semester, and then you have your final exam, which I will post, and you'll have a few days to work on it, and that's it as far as your graded assignments. So anyway, so that's what you have to look forward to coming up. Nothing in the next few weeks other than, like I said, some homework that will be due at the end of the semester. So anyway, I'll see you guys on Thursday.